Namaste. Welcome to our YouTube channel. So today we are going to discuss question number 8 from PSB 2024, where the question says that we have n pairs of observations x1, y1, x2, y2 and xn, yn, and we do not know the exact distribution of these observations or of these variables. But we can propose a distribution for the transformed variable, which is xi to the power alpha, yi to the power beta. Remember that alpha and beta are not known, okay? And the joint density is nothing but bivariate normal with the correlation coefficient rho, where rho is also unknown. Now we need to find out the likelihood function for this model. Now before going deeper into the solution, let us first revisit one simple result, which is regarding the transformation of variables. Now suppose we know that there are variables x and y and the joint density is fxy. Okay, so how can we find out the joint density of w and z, where w and z are functions of x and y, and also they are bijective functions or bijective mapping, which means that if w can be written in terms of x, x can also be written in terms of w, and same for z and y. So there is a simple form that the joint density of w and z can be written down as this, where fxy is the joint density of x and y, and this is nothing but absolute value of the Jacobian determinant. So what is Jacobian determinant? Jacobian determinant is the determinant of this Jacobian matrix, where the Jacobian matrix is basically the matrix of the partial derivatives of the former variables with respect to the transformed variables. So x can be written in terms of w, right? If you take the inverse of this function, x can be written as a function of w. And what we do, we just put x in terms of a function of w here, and this partial derivative will be something in form of w. So this whole determinant will be a function of w and z. Similarly, here also for fxy, if we put x as a function of w and y as a function of z, this fxy will also give us a function of w and z. So this whole thing will be in terms of w and z, and this particular value or this particular expression is nothing but the joint PDF of w and z. Clear? So we will use this particular result in our solution, but before that, let us first understand that why do we need this transformation at all? So the first question is, we know the joint density of xi to the power alpha, yi to the power beta. So what is a likelihood? A likelihood is basically the joint PMF or joint PDF of the observable random variables with some underlying parameters. So when I say observable random variables, it means that we can actually observe the values of the random variables. And since we can observe the values, so in the joint density, the only unknowns are the parameters, and if we put the values of x and y, then the joint density is basically giving us a function of the parameters. That is known as the likelihood. So likelihood is basically same in form with the joint density, but it is interpreted as a function of the parameters because the underlying observations or the underlying variables are already observed. You already have observed some values of those variables. Given those observations, the likelihood give you a function which is basically giving you an idea that how much likely it is to observe this particular values when the underlying parameters are this, this and this. Is it getting a bit complex? Let me just simplify it a bit. So suppose we have xi to the power alpha, yi to the power beta, and we have a joint density where the parameters are alpha, beta and rho. Now if you can observe xi to the power alpha, yi to the power beta and just put the values in the PDF, then what you are left with? You're left with a function of the parameters. You will not have any xi, yi there because you have already put the values. So that function is basically known as the likelihood function for the parameters given the observations. Clear? So for this particular problem, is the joint PDF of this giving you the likelihood function? No, right? Why? Because these variables are not observable. Your alpha and beta are not known, and you cannot actually observe this because alpha and beta are itself parameters. But you can observe is only xi and yi. So we need the joint density of xi, yi to actually find the likelihood function because we can only observe xi, yi. So let us use the transformation to find out the joint density of x and y. So we have the joint density of u and v, which is a bivariate normal, and we need the transformation this. So using the same steps as in the prerequisites for transformation of variables, we'll find out the Jacobian determinant. And remember that here the transformation is bijective. Why? Because alpha and beta are odd. Just like from x to x's cube, the transformation is bijective. From x to x to the power 5, the transformation is bijective. But from x to x squared, the transformation is not bijective. Just rethink this point and it will be clear that why we are taking this particular transformation as bijective and directly using this Jacobian result. Alright. So from this, what we get is the joint density of x and y using those results, the prerequisites that we already mentioned, and the form will be something like this. Okay, we are just putting f u v, and in place of u and v, we are putting the values of u and v as a function of x and y. And also we have the Jacobian. So it will be something like this. So what is the likelihood? Likelihood basically is a function of alpha beta rho given x and y. This x and y are the realized or observed values of your variables. So it will be this. And you have n pairs of observations. So if based on a single pair, your likelihood is this. Based on n independent pairs, your likelihood will be product of all the n likelihoods, which is nothing but this particular expression for all odd alpha beta and for unknown rho belonging to 0 to 1. So we finally got the final likelihood, which is nothing but the joint PDF of n pairs of x and y, and we needed only a transformation from uv to xy. And the concept that to find out likelihood for n pairs, we just need to multiply the likelihoods because the variables, the n pairs are independent. Is that clear? I guess so. So if this problem is clear and if you like this video, thank someone today who is always there for you. Hare Krishna.